Okay, in this second video we're going to start with problem 3, but just to remind you in problem 2 that, or in problem 1, that you need to be able to sketch all basic graphs listed because you're going to be using those in problem 2 as well. So you need to know how to sketch an x to the second, an x to the third, a square root of x, and an absolute value at least. So make sure you look at those those types of graphs, and those should be in section 2.4, part 2. All right, now in this video we're going to start with problem number 3. Write one variable as a function of a second variable and solve. All right, I've given you two examples here. Let's start with the second example. It says we're going to form a rectangle, and then there might have been one drawn in the book. I'm not sure, but we'll draw one just like what it says here. Okay, so we have an x and a y-axis, or x and a y-axis. We have a parabola that starts at, looks like it's an x squared, but it's flipped over. So it goes down like this instead of up because of the negative, and then it's added 10 to it, so it's shifted up to 10 up here, and it looks like it travels like this. I don't have any points on this, and we're not going to be looking too closely at that right away. We're going to do a rectangle inside this. One's on the curve, one's on the y-axis, one's at the origin, and one's on the x-axis. So it looks like this rectangle. So if we look at that rectangle and its dimensions, its area dimensions would be an x value down here and a y value up here. So the area of the rectangle is x times y. Now we're going to want to change this y value to relate to the x value so we can write it as a function of x. So what we're going to do is we're going to try to figure out this point is x comma y, but we know it's on this blue graph, so we can replace y with this equation here, x comma 10 minus x squared. So our replacement of y with 10 minus x squared would give us a function for the area of 10x minus x to the third. Now, we want to know when that has a maximum. So what we're going to do here is use our graphing calculator to figure that out. So we're going to take our function, let's turn that on, take our graphing calculator, we're going to graph 10x minus x to the third, and we're going to look at it. I'm going to look at it at the standard window, so that's zoom 6. We're going to look at the graph. It looks like it has a maximum up there somewhere, and that's what we're looking for. We're looking for a positive maximum. So we need to make our window a little bit taller on the y's. So we would need to maybe make this y max a 20 instead of a 10. And I don't want so many marks, so I'm going to put 2 there for scale. Graph again. So it looks to me that there's a maximum right here. It'll give us a maximum area. So let's try that. Let's find that. So that's under second calculate maximum. We're going to go left bound. We'll get close to the maximum. There we go. Push enter. Go to the right of the maximum. Push enter. Go where we think the maximum is. Push enter. So it looks like our x value here is about 1.825 or 1.83. So x is approximately 1.83. Now, if we know that, then we can plug it in here to figure out what the actual area is. So area would be 10 times 1.83 minus 1.83 cubed. So about, let's see what that is about. 10 times 1.83 minus 1.83 cubed. So about 12.2. So we're going to say 12.2 units squared. So that would be my answer there, or the largest area. Okay, second example, which is actually the first one. It says a wire is bent of x length into a shape of a square. So we have something that's x, and then we're going to bend it into a square. All right, so this is x here. We bend it in a square. So each of the sides of a square is the same. So this is basically cutting into fourths. So each of the sides would be 1/4 x. 1/4 x, 1/4 x, and 1/4 x. Because each of the sides with that. It says express the perimeter of the square as a function of x. Well, we bend it around there. The perimeter is distance around, so the perimeter is x. Or it's 1/4 x added up 4 times. Now the area is taking the length times the width, so it'd be 1/4 x times 1/4 x, or 1/16 x squared. So that's the function in that. Here's the perimeter, here's the area. All right, we're going to move on to number 4. Number 4 says graph a linear function to determine its properties. Okay, so here it is here. We're going to graph the function. All right, so I'm just going to use the slope and the intercept. We're going to start with the intercept here. Intercept is -5, so we go down to 5, 1, 2, 3, 4, 5, and we put a point right there because that's the intercept. Slope is 2, so it's 2/1. So we're going to rise 2, run 1. That would be our next point. Rise 2, run 1. That would be our next point. Rise 2, run 1. So we'd have this line through those points. Okay, slope. So on this one, the slope equals 2, and the y-intercept is 0, -5. The average rate of change is the slope, so this is the average rate of change also. It says graph the function, label the intercepts. Okay, so this one is going to be 0, -5, and let's see, we went, it looks like this one is going to be, so if we were, it went through a half here, so it looks like 1, 2, 3.5, 1, 2, 2.5. And we can double check that by putting in 0 and solving, right? If we did 0 equals 2x minus 5, and we'd solve that, that would be 5 equals 2x. So x is 5/2, or 2.5. So this one is 2.5, 0. And it's increasing. Lines only do one thing. They either increase, decrease, or they're flat, which is constant. All right, so here on this problem, we'll do the same thing. If we have the slope and the average rate of change, and this problem equals -1/3, and the y-intercept is going to be 0, 1. So we're going to start here. We're going to go down 1 and over 3. Okay, and down 1 and over 3. Down 1 and over 3. You can also go up 1 and over 3 to the negative region to get our point. So our line goes like this. If I had a straight edge, it would look a little bit better. So our points are going to be 0, 1 here for the intercept, and 3, 0 for the intercept. It's decreasing because it's going down. Constant would be one that's horizontal. It doesn't have an x if it's a constant one. All right, we're going to move on to problem number 5. Problem number 5, which is Determine whether a function appears linear or nonlinear from a table of values and find the equation. Well, you're going to look at the rate of change here. So we're going to look at this rate of change between each of these points to see if they are the same. So the change here is 5. The change here is 1. Change here is 1. Change here is 1. Change here is 1. Change here is 5. Change here is 5. And the change here is 5. So the rate of change, or the slope, is 5 divided by 1 in every case. It's 5 there, 1 there. So 5 divided by 1. So that's the slope. So our equation on this one is y equals 5x. And then we just need to find the intercept. Well, it's given in the chart right here. Anytime we have a 0 for the x, the intercept is given. This is the intercept. So the intercept is 3. If they didn't give you a 0 number, then what you would do is plug in the x and the y. You would write it as y equals 5x plus b. And then you'd plug in your x and y. For example, if I didn't have the intercept here and I just wanted to use -1 and -2, I'd put in -2 right here and -1 right here, and then we would find out what b is. And b is, we'd add 5 to both sides, so b would be 3. And that's what we had before. But in the chart, it's already given in this one. All right, so let's look at number 5 here. The change here is 7. The change here is 3. The change here is -1, and the change here is -5. Change here is 1. Change here is 1. Change here is 1. Change here is 1. So the first one has a slope of 7 over 1. Then the next one has a slope of 3 over 1. And the next one has a slope of -1 over 1. And the last one has a -5 over 1. So this is not linear, because each time we want the slope to be the same ratio. In this case over here it was, here it's not.